today. We're going to continue what we were doing yesterday a little bit, but yesterday we were doing something called the disc method. The cross sections were discs, like circles, right? Today we're going to do something called the washer method. You guys know what a washer is? All you engineering kids? It's one of those things you put. So for those of you that don't know, it's like that little metal ring that goes between a bolt and a washer. So what do you notice about a washer? It has a hole in the middle. So that's what we're doing today. We're looking at things that have a hole in them. So let me demonstrate for you here. Yesterday we looked at this, okay? And what we did here was I took this graph and we went ahead and we rotated it, right? Let me see if I can get out of here a little bit. All right. It's not. Okay. I'm wondering why. I'm wondering where the interval is. Oh, maybe it's okay. There it is. All right. So now, what I want you guys to notice, though, here about this picture is that the axis of symmetry the axis of rotation is right here.
Yes.
Now, what's significant about that is the fact that the axis is actually a part of the shaded region. Do you guys see that?
Yes.
How it's actually touching that. So what I'm going to do here is I'm going to pull that axis downwards. Make a few adjustments, though. I want you to see something. Get rid of that. So I'm going to take the axis of rotation. I'm going to slide down. You guys see that dotted line? Okay, so I'm going to make that the axis of rotation now. So it's no longer, the axis of rotation is no longer touching the shaded region, which means there's a gap in between the shaded region and the axis of rotation. Okay? And so now when I rotate it, you guys can see now you're going to have a hole in there, right? We'll go ahead and do it and you guys can see it. You see the hole that's generated there? And so it looks like a washer, right? And they call this the washer method. It's really the same shape, but now it has a hole in it. So basically what we're looking at then is that when you do this method, now we have two radiuses, okay? We have the outside that goes to the center, right? And then we have the inside circle. So there's two circles, so there's two radiuses, right? So now here, like the distance from here to the axis, we would call that the big radius, right? And the distance from this curve to here, that would be our little radius. Okay. Now, really quick, if I asked you guys to find the area of a washer, what would you do? We'll call the big one. Yeah, you do. So what we would do is we would find the area of the big circle, right? So what's the area of the big circle?
Big R minus little r. R squared.
So the area of the big circle is just pi big R squared, right? And the area of the little circle
is pi little r squared, and then you subtract.
There you go. So pi little r squared, right? And then the area of the washer then would be what you get by subtracting those from each other, right? So if you were to subtract the area of the little circle away from the area of the big circle, you end up with what's left, the area of the washer. Okay? So that's what we'll be integrating. right? Because now every cross section on this shape over here, every cross section is a washer. So if I find the area of one washer and then add up all the washers behind it, we're going to end up with the total volume of the shape with that hole in it. So we're going to take pi big R squared minus pi little r squared, and we're going to integrate it. And that's really the only difference for what we're doing today. But how do you, but the thing that I want you to be aware of is that how do you know when you're doing the washer method or not? And the answer is, where's your axis of rotation? Is it actually touching the shaded area, or is there a gap between the shaded area and your axis? If there's a gap, then you've got a hole in it, and that's a washer method. You're going to have a little radius and a big radius. So that's what we're looking at today. So just for the sake of our notes, I'm going to go ahead and write like something like that out for you guys. I would encourage you to write that down in your notes. Let's do it. All right. So let's say that we have a curve. We'll call it f of x. And let's say that we have another curve. We'll call it g of x. Now I could have done a flat line, like on the last one that I just did. The bottom line was a flat line, right? But it doesn't have to be. It could be anything. Yes, sir. Okay. And then what we're going to have is we're going to have an axis of rotation. So on these, we're going to have two different radiuses, right? We're going to have a big radius. And we're going to have a small radius or a little radius, whatever you want to call it. So the big radius, we're going to call that r of x. And r of x, it's the same thing that we did last time. It's the distance of your line that's on top from the axis. Okay? So that would be f of x minus the axis, right? Or like we talked about yesterday, if the axis is above it, it would be axis minus the function. The little one, the little radius, is going to be the distance from your curve on the bottom, the one that's closer to the axis. That's our little radius. So I'm calling that g of x.
Is there always going to be an f of x and a g of x?
There would have to be.
For the washer method?
There would have to be. One that's further away from the axis and one that's closer, so that there's that hole in the middle. And I guess you could say that that's a distinguishing difference between the washer method and the disk method. All right. Now, as you guys know at that point, now this is getting kind of ugly, so I don't know if you guys want to draw this next part. But what we do is we rotate it, right? So I'm going to rotate the object. That's kind of like what f would look like. I don't want to go any lower than that, but that's what it would look like if I rotated that. And then if I rotated the g, be a little bit smaller, right? So you end up with this hole in the middle. So now we talked about how to find that, the area of the washer. The area of the washer would be pi big R squared minus pi little r squared. The area of the big circle minus the area of the little circle. And therefore, if you wanted to turn this into a three-dimensional image, the volume would be pi big R squared minus pi little r squared integrated.
Can you take a pi out? Yeah, can you take pi out?
Sure.
Can it be pi with the second?
No. You could just take out 1 pi and put it in the very front. So while we're on that note, let's do that. So, because actually that's what they usually do. Usually they do, you'll see it written like this in books. I like to write it like I have up there because that makes it kind of connect the idea that those are both little areas we're subtracting. But this is actually a very common way to have it written is they just factor the pi out of the whole thing. So I don't mind if you guys do the same thing. Okay? That's that.
Do you want us to add there or do you want us to actually solve?
This is just a formula. We're not using any real numbers here.
I know, but like when we have real numbers.
Oh, when we do it, you can stop there because at that point it's all review. So I'm good with stopping. What's up, Dev?
Oh, never mind. I'll just add the 5 to out. And then on the test, you want us to actually like solve.
No, actually, I made your test already, and I'm just gonna have you do the setup for the.
Okay, so it's set it up like that pi.
So that's the same for homework too.
I don't care. Yeah, if you want to do it for homework, it's fine.
We don't have to do that.
All right. So let's go ahead and actually do some problems then, and we'll begin our lesson. So go ahead and find number 1.
I think I found it.
You know what? Your precious A minus will be
That is not on our piece of paper. That is not number 1. That is number 2.
All right. So where is my axis of rotation?
X.
Quiet, please. So is it touching the shaded area? So that little shaded area, if I'm rotating it around, you guys see that's where the gap's going to be. There's a giant hole in the middle there around that axis of rotation. So this is the washer method. So that means that we have to find a big radius and a little radius. Now, this curve right here is kind of hard to see because it's so small, but from here to here, that is the line, that's the curve that is farthest away from the pink line. So that one's going to give us our big radius. So let's do the radiuses now. So big R is going to be this curve. What's the equation of that curve?
X squared plus 2.
Minus the axis. What's the axis? So it's x squared plus 2, right? Now let's do the little radius. There you go. The little radius is
2.
this guy, yeah. That's our little curve that's closer, and so that one has a radius of 2. I'm sorry, not a radius. It is 2, and we're subtracting the axis from it, so yes, it's just 2. Okay? So now we're going to do our setup. The area of the cross section would be
Pi big R x squared. Well, you plug it in. My bad.
I will. I'm going to write it like this first.
You're welcome.
Okay. Right? So this is the area. And so it's going to be pi x squared plus 2 squared minus pi 2 squared.
Oh.
All right. And then finally we have volume, which is going to be the integral with, we'll go ahead and put the pi on the outside.
X squared plus 2 squared. You've got squared.
What happened to your square? And then why did you put a pi on the outside? Why did you put a pi on the inside? My bad. Or pi.
Oh, you're right. Yeah. With that pi won't be there anymore, right? Because I took it out.
That's a point from one.
It is a point.
What about my point part of the square?
Sorry.
Yes.
0
Thank
to
you.
1.
Yes. Very good. All right.
Why do
So
you have
now
it in the- why do
the
you have it in the
limits.
square
0 to 1.
We're going from what to what?
0 to 1.
0 to 1.
Why do you have it in those square brackets?
I've already got parentheses, and so I use brackets sometimes.
Why?
So you can differentiate.
Yeah, it helps differentiate.
What's it?
Yeah, go ahead.
That's fine.
We're good? All right, and once again, we're not going to actually find the volume, but there it is. And this shape, just to kind of help you guys along with your visualization, you know, we have a shape that looks like this, right? Now, if you were to rotate that, what that might end up looking like is something like, kind of like a trumpet almost, right?
Oh yeah.
Yeah.
It's a wizard's hat. Oh yeah.
Oh.
That too. A wizard's hat.
It's
All right.
a black hole.
I don't know about that.
Actually, that's actually
I know.
Okay. You go. You go. Okay, I'm going to ask Thomas. Thomas, what is, you were gone yesterday, so this might be a little rough for you, but what's our big radius?
negative x squared plus 4.
It is.
Gee, it's like I told you the answer.
Okay, now let's see why it is, because here's my axis of rotation. I've got two curves there. One's here and one's here. The one that's furthest away is the one on top, and that's the parabola, so that would be negative x squared plus 4. All right, next one. Nick Del Rosario, what's our little radius?
Negative x plus 2.
I agree.
He agrees.
I agree. Now, really, we're supposed to subtract the axis from it, right? But my axis is 0, so I'm just kind of skipping that for now.
The reason why it's a big R is because it's on both. It's the curves.
No, not because it curves, but because it's further away from the axis of symmetry. This line is farther away from this line than that
I
one.
see, because it's under.
Yep.
Got it. Okay.
All right. Next, we have the area. So I'm going to ask Brandy, tell me what the area of the washer would be, please.
Yeah. Yo,
Cool.
Brandon, you're so smart.
And then next step, how do I turn this into a volume by integrating it? Yeah, well, just like tell me what to add here.
Oh, you added the integral sign, and then the limits -1 to 0,
And that's
and
it.
then dx.
I'll see if the pie's in there this time.
I was about to say that.
Why not the cakes?
Not sure what this thing would look like if you actually tried to graph it. All right, let's do another one. Why don't we see if you guys can do this? It was going to be a teacher example, but I feel like you guys have probably got this.
We got this, bro.
Go for it. The big radius. So our big radius would be negative x squared plus 6. She's right, because this is my function, and you subtract from it the axis, and you get 6. Okay. Next, William. I know I'm coming at you a little bit out of left field because you had some issues there, but so little r is going to be what minus what?
3 minus 1.
Okay, so 3 is this one, and 1 is this one, so we're finding the distance between them, yes. So that would be 2, right?
Nice job, Will.
All right, so I'm going to ask Sean to share with us his final answer at this point.
Okay. Pi.
Oh, just, okay, pi.
I thought he said
Okay,
hi.
sorry. Equals pi multiplied by the integral from 0 to 2.
No, it's 1 and 2.
No, 1 to 2.
Just go ahead, Sean.
Okay, 0 to 2.
I'll look at it.
In parentheses, negative x squared plus 6. End of parentheses, squared minus 4. Dx.
No, the x-axis is 1.
All right, so let's take a look. We're going from 0 to 2. 0 to 2.
Oh. Oh, yeah.
All right. Let's do another one. I wonder if We're going to skip number 4, so if you guys want to put an X through that, you can. Let's take a look at number 5. All right. So I feel like we're kind of just getting to the point where this is boring because it's too easy for you guys.
No, I don't get the Y one.
So I'll do an example and then I'll let you guys do 2 and then we're going to be done.
Yeah, we can go home.
This is actually our last normal calculus lesson. You know, right?
I'm not ready, Dad!
Okay.
Wait, do I have a test tomorrow?
All right. No, but it's review. All right, so let's do some work. I'll do this last example, and then I'll let you guys do a couple practice problems, and we'll call it a day. So, here's the region that I'm rotating, correct? Shh. The axis I'm rotating is here, so you could tell by that little swirly thing there. And once again, there is a gap between the region I'm rotating and the axis, so this is a washer method, right? Which means we have a big radius and a little radius. Now, I've got 2 curves here. I've got this curve on the right and this curve on the left. The one on the right is further away from the vertical axis, right? So that distance is the big radius. From there to there, right? And so the way that we find that is we do the function once again, which is, it's all, matter of fact, I have something wrong here, but it's not quite that.
It's R of Y. I said that.
It's R of Y. And they've already gotten the X by itself, so it's already in terms of Y for us. So we have, there's our function minus the axis, which in this case is negative.
Just 0.
Oh, is it just 0?
Yeah.
0. I don't get it.
Yeah.
Okay.
Alright, that's 0. And then little r of x is 1. Or y.
Yeah, so little r is the distance. It's really, I'm not going to be able to label it very well, but it's the distance from this flat line to your axis, and that's a space of 1. So I'll try to label it as best I can, but it's little r of x there, it's 1. Now the way you would show your math, though, is this line is represented by the equation x equals 1. So that's my function, minus the axis, which is 0. And so the answer is 1. Okay. From there, we just go ahead and but what are my limits of integration?
0 to 4.
0 to 4. Okay, so here's what I'm asking you guys to do. I'm going to ask you guys to do 6 and 8. And is that all that's on the worksheet? Stops at 8?
No,
10. Okay, we'll see what's up with 10 in a minute. For now, go ahead and do 6 and 8, please. 6 and 8. Okay. So Lucio, on this problem, what's my radius? Big R.
Which one? 6.
Are you Lucio?
6.
I'm talking to Lucio.
Oh.
So Lucio, what do you think? Okay, good. So my radius that's the biggest is 6 because it goes from here all the way over to that axis. That's the longest radius, right? That's what's getting rotated around that axis there. All right. Art, what's the little r? Shh. Shh. Say that again. Okay, so that's this one. So that's the distance from this curve to this line. So that's radical y minus 0. And that's a shorter radius, right? So that one's also getting rotated around. Oops, went too far there.
Oh.
You guys can kind of see the shape there a little bit, right?
It's like a lava cake.
Yeah, it does look like a lava cake. Good comparison. All right. Okay, so Daniela, what's the formula for the volume then?
5 times the integral from 1 to 4 parentheses 36 minus y.
Oh, I guess you don't need to.
Yeah.
Sorry, let me. Anyway, so minus y and then what?
dy.
Cool. All right, I feel like when I was coming around checking, I feel like there were some people that had y minus 36.
No,
If-
that's wrong.
That's
Okay,
making- that's making
so
it
make sure you have this order because this is correct. All right. Okay, number 8. David, big R.
Oh, it's y squared plus 2.
Good. So you take this and you subtract from it this, right?
Isn't the 3 closer to it? No, the axis.
The 3 is closer to it.
Yeah, the 3 should be the big R.
No, 3 should be the
No,
closer.
way.
I think you're wrong.
Big R is
Now I'm feeling like it's not 2. I'm feeling like it's plus 1.
It's 1.
It's minus 2.
It's minus.
It's 4 minus 2. Yeah, isn't it 2?
Oh, I thought
it's
minus 2.
Yeah, minus 2.
The
axis is 2.
I can't listen to everybody talking once. So maybe can somebody explain it to me? Go ahead, why?
The axis is 2, so it's
The axis is 2?
Yeah, the axis
Oh,
is 2.
see, I was looking at this. Okay,
You silly dude.
you are right. Did anybody else out here put 1 for their answer there? I feel like I saw that somewhere. Okay, so it's this minus
Oh, I
this
had,
then.
I had,
You had 1?
I had little r equal.
Oh. So there's that, and then we have little r.
1 equals 1.
There's your 1.
That's 1.
Maybe that's what it is. So the distance from this line to this axis here is 1. All right, so we'll do one more call out here. Aaron, what's the area or the volume of this solid then?
Pi integral 0 to 1.
No.
Oh, negative 1 to positive 1. Y to the second plus 2 squared minus 1.
Okay, cool. And that's that. This would be kind of a cool looking shape. It would look like this on the top and this on the bottom, but then it would cave in on the sides. You guys see that?
It's a tabletop.
Of course, there's going to be a hole in the
It's a
middle.
yo-yo.
Like a yo-yo.
I said
That looks like my toilet.
The ones that are giving the interior side. Oh my
You want to draw it? That's a problem for today. Quiet, please. Okay, so just like yesterday, although this thing has some interesting stuff associated with it. So let me kind of guide you guys with some questions through this one a little bit. First of all, is this a dx or dy integration? Okay, so someone with one hand, one person here. I'm going to ask Jordan. Jordan, why do we know this is a dx?
Because you can see that the axis of rotation is on the x-axis.
There you go. So the way you can tell is because the axis of rotation is horizontal, right? So that's a dx problem. Now, what does that mean about my equations? Yes?
You have to get the y to the other side. Yeah, respect to x, not y.
It has to be with respect to x, not y. So these are backwards, and we need to fix them. So I'm gonna let you guys go ahead and fix them for me real quick, and I'll ask you what they are. So go ahead and fix them. What did you get for this one?
Y equals 2x.
y equals 2x. Isn't it minus 2 though?
Yeah.
Okay.
2x minus 2.
And then I'm going to ask Luke, how about this second one?
X squared minus.
Okay, so we had to do that because my axis is a horizontal axis. You got to keep an eye out for that kind of stuff. All right, so now we're getting the next question. Big R versus little r. Now, some of you guys already have it, and some of you don't. So, how many of you guys have already thought about it at least? How many of you have not even thought about big R yet? Okay. So, see, I'll give you like 30 seconds. See if you can figure out what big R is if you haven't yet. It's a little bit tricky, though. There's something on here that we haven't seen yet. But go ahead and take a... I'm going to ask Noah, what is the big R here?
The x squared minus 4. Or x squared minus 2.
X squared minus 2.
Yes, no.
Well, you're close. You're close.
The other one?
But, so you've picked the right function, but that's not what the radius is. So let me help you guys out a little bit here. Remember how we talked about the one that's furthest away from the axis of rotation? That's the one that is the big radius. So take a look at my two curves here. I've got this parabola here, and then I have this linear function above it. Right? Which of those lines is farthest away from that dotted line up there?
The green one.
The green one, right? And that's the x squared minus 2, so he's right there. But remember, your radius is the function minus the axis, right?
Yep.
So what is the axis?
2.
2. But is it always function minus axis?
No.
When is it axis minus function? When the axis is above it. So actually, here's how you guys would set this up. The big radius is the axis minus the function. And so that's going to be 2 minus...
Squared minus 2. And then you change the signs. It becomes negative x squared, and then when the positive 4x. So x squared plus 4.
There it is. There's your big R. That's a hard one. All right. I want you guys to do little r, and I'll call on you for that in just a second. Find little r now.
No, I told me if the x-axis is on the bottom, and so big R would actually be the little r. With that, then that's the time you would subtract it because it's below the axis.
Yeah. There you go. I think you got the right idea. All right. So now I'm going to ask Moises, what's little r then?
It would be negative 2x plus 4.
Yeah. If you want to see the rest, I'll pick the answer up really quick, but at that point, it's all the same. There's nothing new here. All right, guys, we'll see you tomorrow.